start just now. Okay, let's wait 15 seconds. Okay, good afternoon. Welcome to the third lecture in this mini school series. My name is Francesco Petruccione, and I have the pleasure again to introduce you to you today's speaker, which you've met already twice, Dr. Sahal Yacoob from the University of Cape Town. Yeah? And Sahal will continue today where he left last week. And Sahal, we are very happy for you to be back with us. We are very grateful also to the participants to be so loyal to this school. And Sahal, please, if you would like to share the screen, you're welcome to start.
Okay, great. Thank you very much. I want to thank everyone for coming back while I set up my sharing. Okay, can you see my screen?
Yes, yes, thank you.
Lovely. Okay, so as usual, please ask questions as we go along because I'd rather not lose you early on. And the first thing I'm going to start with is your homework problem. So I hope everyone did their homework. And the homework was, if the Large Hadron Collider collected 25 inverse femtobonds of data, how many proton-proton collisions have they produced? Now we should hopefully remember, or at the very least, I should know, that the total number of collisions is going to be the cross-section times the integral of the instantaneous luminosity with respect to time. And what we're being told already is that this is 25 inverse femtobonds, and this is 100 millibonds. And we just have to multiply them together. And honestly, it shouldn't be hard, but to be perfectly honest, this -1 up here on the inverse femtobonds is something that took me ages to sort out. But if we do it simply, we get n equals 100 times 10 to the -3 bonds, and then we're multiplying that by 25 times 10 to the -15 bonds, but the inverse applies to all of those, and so our inverse bonds and our bonds cancel out, and we get 2500 times 10 to the 12. I've done that right. Events. So if that was trivially boring for you, I guess it didn't take too long. And if you got a little bit confused with the units, then yeah, don't feel bad. That happens to all of us. Just some reminders of some ideas we went over last week in the last lecture because we didn't really get to the end of it. Our interaction rate is defined by an amplitude, which includes the probability of a transition from our initial state to our final state based on a potential, times some phase space integral, which is the bit that takes into account the kinematics of the problem. What are the initial and final momenta and energies of the particles. And generally, we will describe a system as 2 incoming particles, 2 outgoing particles, and then a process will happen in the beginning. And that's a standard thing we're going to stick with. And the kinematic information of the interactions is encoded into the 4 momenta of the 4 particles in our system. We spoke last week about the Bourne approximation, and then there's some maths that we're not going to do. And I told you without much proof that, well, it's an honors level course to work through the proof usually, that the rate for a particle to decay into its daughter particles, so particle A going to B and C, has this bit, the square of the matrix element, which depends on what these particles actually are, and that the physics will tell us if it's allowed, it can handle. And then this other piece, which contains the kinematics, this is evaluated in the rest frame of particle A, and this momentum is the momentum of particle B or particle C. Because we're in the rest frame of A is at rest, and conservation of momentum tells us that these particles must be back to back. The total energy of the system is just the mass of particle A because we're in the rest frame of A. Similarly, for a, let me just mute my computer. Similarly, for a 2 to 2, oh, I can't mute my computer because then if Ilya wants to interrupt with a question, I won't be able to hear. So we're gonna have to put up with hearing when I get emails. On the bottom, we have a 2 to 2 scatter where incoming particles A and B become outgoing particles C and D. And there's a similar structure. We have 8 pi squared instead of just the 1/8 pi that comes from the extra particle. Essentially, we have the total energy squared, which in this case is the sum of the energies of our incoming particles rather than just the mass. We have the matrix element telling us about the physics. And now we also have the magnitude of the momentum, the 3 momentum of the final state particles, divided by the magnitude of the 3 momentum of the initial state particles. And this, again, is in a particular frame. This is in the center of mass frame. And of course, it doesn't matter if we call it the center of mass of the initial state or the center of mass of the final state because they're conserved. So it's just the center of mass frame at any time. Right. So our matrix element can be calculated from the Feynman rules. I'm not going to say too much about this. I didn't really want this to be back in here. I did want to talk about how we calculate the matrix element. So the matrix element calculation is an integral, but to know exactly what integral we want to write down, we can determine from these Feynman diagrams. So these Feynman diagrams represent the terms in the Lagrangian that were psi bar, gamma mu, psi a mu, and what they're telling us is there is a photon, there is one lepton field, and there is a second fix my handwriting. The second lepton field. And that's what we see in all of these cases. We see our one photon, and then two leptons. So this vertex is described by this term in the Lagrangian, depending on what these lepton fields are. So in this case, we have an incoming particle, an outgoing particle, and a photon being absorbed. In this case, an incoming particle, an outgoing particle, and a photon being emitted. And here we have an actual complete interaction where we have two incoming electrons bouncing off each other and moving away. Time flows from left to right, and the vertical axis doesn't really have physical meaning. And these arrows tell us whether we're looking at a particle or an antiparticle, and that goes all the way back to lecture 1 and our identification of the antiparticle fields as negative energy fields going backwards in time. So that historical idea carries through in the way we draw these lines to identify what's happening. Okay, where we ended last week was here. So hopefully all of this has been familiar to you. We saw that at this vertex, this photon had to be massive, and that's called an off-mass shell particle because physical photons are massless. The initial and final state particles of any Feynman diagram are real. This is not a complete Feynman diagram, so there should be something else on the end. And the virtual particle can be unphysical. It can have this off-mass shell value, this extra energy, as long as the combination of the amount of energy that it's borrowed and the amount of time it's borrowing that energy for is limited by the Heisenberg uncertainty principle. And we're going to talk about that on the next slide. But this is where I ended at the last lecture. And I know I did the last few slides very quickly. So I would like to pause here and ask if there are any questions before continuing. Ilya, I assume there's nothing, or?
Inji is raising his arm. I will allow him to talk. Inji, you can unmute.
Hello, hello, Hi, Sahal. Very interesting lecture. So, may I just ask a quick question at the beginning of your second lecture, which you derive the cross section, and you emphasize that the cross section is only meaningful in terms of scattering. So, there is no cross section for a single particle. So, I think I understand that. But later on, you derive the cross section for an event that you eventually reach a formula of sigma equals to pi r square. And that does means a surface area of a single particle, right? So how can, I mean, basically, if I understand your previous claim that the cross-section could vary for a single particle, for different scatter event with different particles, the cross-section could vary. In what sense that could vary? In what sense that the cross-section is not equal to the geometric area of the particle? Yeah, I think that is my question.
Thanks, Shinji. I'm sorry about that. Yeah, I mixed two ideas there. So my initial point, you're right, is that within particle physics, the cross-section is a property of the interaction. But then I did take a couple of slides and I spoke about the classical mechanics hard scattering cross-section of a point particle of a solid sphere, just to talk about it. So that where we got the pi r squared out of it, that was just classical scattering between two particles. And in that case, with a point particle of a hard sphere, we do get pi r squared. But if we were scattering two physical spheres, for example, we would not still get pi r squared, right? So even in the case of classical hard scattering, the effect of cross section for a collision depends on both particles. We think of it automatically as a point particle of an extended particle, but even in classical mechanics, that's not really the case. So I said something about a cross section being something that talks about the rate of interactions, and then I tried to tie that idea back to classical mechanics scattering of a solid sphere. But those are separate ideas that I was using just to illustrate that, yeah, to tie what I was talking about back to something that I thought students might be familiar with, which was why I did that. Is that
okay? Thank you for your explanation. Thank you. Yeah.
anything else?
Not. I think you should continue.
Yeah.
Thank you.
Well, anyone else, I guess, Ilya. Oh, was that you, Ilya, saying I should continue?
Yes.
Yes, please go ahead.
Okay, I am going ahead. So now we're going to look at the range of a force mediated by a massive particle. So here we have some undefined interaction. We have particles A and B coming in. They interact by exchanging some unknown boson that is called X, and then they move away from each other again, unchanged particles A and B. What we're going to do for this treatment is we're only going to consider the bottom vertex. And we're going to consider this slightly different to how it's drawn. We're going to consider this with a bit of time added in. So we have our X, and so we have our particle A absorbing particle X and moving off again as particle A with a different momentum. If we want to look at, we're going to consider this, in the rest frame of the initial particle A. So PA initial is equal to 0. That means our initial energy, our initial state 4 vector is just MA and 0. And our final state 4 vector is, hang on a second, I might have done this entirely the wrong way. Let me think about this. Yep, that will make a bit more sense the other way. I'm sorry, I got ahead of myself. But this will make more sense. We have our initial state particle, and it radiates off particle X. There we go. And we start in the rest frame of A. So in our initial state, we have a 4 vector MA at rest. In our final state, we have particle A again with some different EA and momentum PA, and particle X in the most general case with energy EX and momentum PX. If we look at just change of energy, it's final minus initial, so EA plus EX minus MA. We know that E squared is equal to P squared plus M squared. And so we can make that substitution back into here. So this is our expression for EA. This is our expression for EX. And then the mass of A stays the same. We've done some extra things in here. we've basically imposed conservation of momentum. If we start in the rest frame of A with 3 momentum 0, then px must be minus pa, and px squared will be pa squared. If we consider this term, if pa squared goes up, the amount of energy we need to borrow goes up, right? This term is positive, this term is positive, so we need more and more energy for this to be the case. So the limiting case, the minimum amount of energy we need to borrow for an interaction to be mediated by particle X is in the limiting case that PA goes to 0. If PA is 0, this is MA plus MX minus MA, and we get that our change in energy is always at least the mass of our mediating particle. So if everyone's okay with that, we can then turn ourselves to the Heisenberg uncertainty relationship. So delta E, delta T greater than or equal to 1/2. This means delta T is greater than or equal to 1/2 delta E. What this tells us is we can borrow energy up to the amount delta E as long as we don't look at the system for longer than the value delta T. Okay, so remember, this equation sets the limits on what we can measure. So we won't measure an energy violation, delta E, if we look at it for an amount of time greater than delta T. I know the relationship signs look wrong, but it's about the interpretation and the mathematics. So that tells us that for any given violation of energy conservation, there's a minimum time over which we can absorb the system, and that's given by 1/2 the mass of the particle. And because hy equals c equals 1, that time is also a distance, because time times c will give us our distance scale. And this gives us the range of a particle. So a massive mediating particle will be able to act, will be able to carry the information about the interaction it is mediating over the distance tau or over the time tau. And that's why, for example, the electromagnetic force has an infinite range. This is one of the reasons that when we think about putting gravity into this framework, we think that the graviton must be massless, because gravity has an infinite range. And this is why the weak force is so weak, because the mediators of the weak force have large masses and therefore act only over very short distances. Some useful things to talk about when considering interactions are the Mandelstam variables. And Mandelstam was a South African who obtained a BSc from Wits in 1952. When we're describing 2-to-2 interactions, which is basically how we talk about most things, the Mandelstam variables tell us about the momentum being carried by the boson. So if we look at our first diagram, which is an electron and a positron annihilating to form a photon, which then pair produces. Okay. This is called an S-channel diagram because the momentum carried by the intermediate boson is the sum of the two incoming 4 vectors. The T-channel diagram is described by the boson carrying the momentum that is the difference between particle A on the top left and particle C on the top right. So that's how much this boson is carrying away. And the U channel is interesting. It looks like I might be playing a trick on you. The U channel cross section is where we look at the difference between particle A and particle D. And the fact that the U channel is different to the T channel has to do with how we do the calculations. We do integrals over the four momenta of A, B, C, and D. And that's why PA minus PD is slightly different. And so this is a slightly different diagram, but this diagram can only exist if the particles in the initial state are exactly the same as the particles in the final state. They have to be indistinguishable. Otherwise, this diagram can't be drawn this way in a way that makes any sense. I'm doing this quickly and I'm happy to take more questions on it. But the important thing is that it has to do with the labeling of particles and the probability of a particle with momentum A being measured finally with momentum D, as opposed to momentum A being measured with momentum C. And that all goes into the energy and momentum conservation. So with that background, we can start to understand QED. So in quantum electrodynamics, we have the term that I spoke about previously, possibly a bit too early, which is this psi star gamma mu a mu psi. And this is our basic diagram. Okay, we have an incoming lepton, an outgoing lepton, and a photon. There's always two solid lines and a squiggly line. And every time we have one of these vertices, that means there's an interaction mediated by a photon, and we get this alpha equal to 1/137. And there's power in this. Again, it's beyond the scope of what we're doing, but by building up interactions from these diagrams like Lego blocks, we build up all the electromagnetic interactions of nature. If we look at the pieces of the interactions, we can get different pieces by rotating the diagram. So this is an electron scattering off something because this photon has to have a source somewhere off the screen. So this is an electron scatter. This is an electron and a positron annihilating. The arrow there is in the forward time direction, so that's the electron. That arrow is backwards in time, so that's the positron. This is a positron scatter because of the arrows on the lines, and then pair production. And in the Lagrangian, that would just be different spinors that describe the different particles that we have. So here we have complete interactions. So I will run through them, or you should work through them on your own if you're getting a bit tired of my voice droning on. We have an electron scattering of a muon in the first diagram. In the second diagram, we have an electron scattering of an anti-muon, positively charged. In the second diagram, in the third diagram, sorry, we have a muon and an anti-muon annihilating, and then creating a down anti-down quark pair. So this is the first time in QED that we're showing quarks. But remember, the quarks have electromagnetic charge, so they interact with photons. Our fourth diagram on the top right looks kind of different. This is the first time that we have final state photons and an intermediate state lepton. So in this case, for example, whatever this lepton is, it's virtual It doesn't need to have its physical mass. And we see that we have physical photons, so these photons must be massless. And so even though the boson that mediates the interaction for QED is always the photon, there is this allowed interaction that's really kind of mediated by the lepton, which is a little weird, but this is an electron and a photon scattering off each other. Then down here we have E plus E minus going to E plus E minus, and this can happen in both the T channel and the S channel. And then finally EE going to EE, and here we have the T channel and the U channel diagrams, right? There's no S channel diagram because two electrons cannot annihilate, and there's no U channel diagram on the left because we always know in our final state there is an electron and a positron, whereas in this case there are two electrons and we don't know whether the electron on the top right was initially the one on the top left or was initially the one on the bottom left. Unfortunately, that's not the full set for any interaction. The previous examples are what are called the lowest order diagrams for a process. The order has to do with the number of factors of alpha that are in the calculation. For every process, there are higher order diagrams. So if we look at E mu to E mu, so going back, that is our first diagram on the top left. This is our leading order diagram. We got a factor of alpha from that vertex and a factor of alpha from that vertex. So this cross section will be proportional to alpha squared. Well, that diagram will be. But these other diagrams have exactly the same initial and final states. Right, so let's look at the initial state. In all of these diagrams, it's an electron and a muon, just like here. Let's look at the final state. Also an electron and a muon, just like here. So quantum mechanically, these are valid ways for us to start with an electron and a muon and transition to an electron and a muon with different momenta. So all of these processes contribute, and they're made up of just adding more of that same vertex, two lepton lines and a photon. So these higher order diagrams are constructed by adding additional internal lines without adding external lines. And each vertex adds a strength proportional to alpha. And when we want to calculate something, we have to add up all the diagrams. Okay, so we start with our leading order diagram, then the next leading order diagram, then the diagrams at the next order with more internal lines, etc., etc., etc. But luckily, alpha is 1 over 137, so each order contributes a much smaller amount to the result. And so for most processes in QED, the leading order diagram is sufficient. And then as we start to measure things more accurately, we need the higher orders. That's it for QED. Then we can go onto the weak interactions. It's a similar idea. The weak charge is a bit complex, so we're not going to talk about it too much. All the fermions carry the weak charge. The weak bosons, there are 2 of them or 3 of them, depending on how you count. So there's the W and the Z bosons, but the W exists in 2 flavors. There's the W plus and the W minus. Because the W has electric charge, it has an antiparticle that has opposite charge. The W boson couples charged leptons to neutrinos. So we see that down here in our middle diagram. On the left, we see the Z boson coupling a fermion to a different fermion. or to the same fermion, I'm sorry. And on the right, we see the W boson coupling a quark with charge -1/3 to a quark with charge 2/3. So these are the three weak interaction vertices. And of course, just like with the QED vertices, as we rotate them, the meaning of the interaction changes. So here we have a few weak interaction examples: an electron and a muon bouncing off each other, just like we've been considering in QED with the photon. That can also happen with the Z boson. Here we have a D quark interacting with an electron neutrino to give us an up quark and an electron. And down here we have some baryonic interactions that we're describing in the same language. So we're starting with a neutron on the left, 2 down quarks and an up quark. One of the down quarks transitions to an up quark, emits a W minus, and that W minus decays to an electron and an electron antineutrino, which is beta decay. And here we see the lambda, which is a particle made up of an up down and a strange quark, decaying to a proton, 2 up quarks and a down quark, because the strange becomes an up, emitting a W boson, and that W boson decays to an up and down pair of quarks, which is a meson called the pi zero. So these are the fundamental interactions that take place when we see these nuclear interactions between bound states. And finally, we get to quantum chromodynamics, the most unusual interaction that we're aware of. It describes the strong interaction mediated by gluons. The charge of the strong interaction is color. There are 3 types of color: red, green, and blue, plus their anticolors. And when I say there are 3 types of color, that's not like thinking of electromagnetic charge as having 2 types. Electromagnetic charge has 1 type that can be positive or negative. Color has 3 types that can be positive or negative. So you can have positive red and negative red, positive green and negative green, positive blue and negative blue. Only quarks and gluons carry the color charge. There are 3 fundamental QCD vertices. There's one that looks very much like the QED vertex with quarks and a gluon. But because in this case, our mediating particle, the gluon, carries the charge, we have these additional diagrams where we have a gluon vertex, a 3-particle gluon vertex, and this one really unusual one, which is 2 incoming gluons interact directly and scatter off each other to give 2 outgoing gluons. Just like QED, when we want to calculate something that's an interaction that's been mediated by the strong force, we piece together a complete interaction by adding these vertices together, and we have to add all the diagrams with their internal lines. And that becomes a problem because the strong coupling constant is a 4-to-1. Remember, alpha was 1/137. The higher order diagrams gave us more factors of alpha, and because there were more factors of alpha, they were suppressed further. With the strong coupling constant, because alpha is approximately equal to 1, that doesn't happen. So in principle, we need to sum everything. We're saved because of these 2 ideas, 2 characteristics of the strong interaction. The first is the idea of asymptotic freedom. So asymptotic freedom is the idea that as color-charged particles get closer together, the interaction between them gets weaker. And in our case, closer together means an interaction that happens with high momentum transferred. And that's why we build large particle colliders. That's one of the reasons we build large particle colliders, to get our colored objects moving with high momentum. So when they interact, they're interacting with a large momentum transfer, and they're doing that then in a regime where we can perform calculations. Because we have to do the calculations perturbatively, we can't do these infinite sums, and we can only do that at small distances because the coupling constant for the interaction becomes smaller. And this is really weird. This is a crazy new idea, right? We have our two quarks close together. I think I spoke about this in the first lecture. And if they're infinitely close, if they're, you know, just barely separated, they won't interact. They will think they're alone in a room with the other quark behind them. And as they turn around, the other one turns around and they're not there. And as you start to separate them, the interaction between them gets larger and larger and larger. So this idea is asymptotic freedom. The other thing that's weird about the color force is that the colored interaction is that we don't find naturally occurring particles that carry color. So color is hidden. Quarks are confined to bound states with no net color charge. That's why we find them in sets of 3. We have our red, green, and blue, which add together like the primary colors to give us something colorless. That's why quantum chromodynamics and the charge of color is used. Or if we have bound states of 2 quarks, a quark and an antiquark, there'll be red and an anti-red. And this weird idea of confinement means we can't do the thing that we did with electrons, for example, where we just took an electron, a single charge carrying particle, using electric and magnetic fields. We isolated the electrons and studied how they behaved under various stimuli. With quarks, we can't do that because we can never get a free quark. They're always confined. Hadrons are particles made of quarks. A meson is a hadron made of a quark-antiquark pair. A baryon is made up of 3 quarks. Here's a list of some baryons and mesons for you. I've gone a bit slower than I planned as usual. I hope you haven't been bored. So I'm going to skip ahead a bit.
Sahal.
Yes.
There is a question which we can also attribute also to the current slide. Does the gluon Feynman diagrams always show as a circular line?
Yes. So we use, generally we use, that type of line is a photon. That type of line, and we'll write W/Z on it, will be a W or a Z. Then the dashed line will be a Higgs. And the telephone wire will be a gluon. That's just a convention.
Thank you.
I think I'm going to skip ahead for a couple of slides because I want to talk about the evidence for the things I've been telling you. So what is the evidence for quarks? We can't isolate these quarks. We can't put them in a box. So why am I confident telling you that they're there? And this is because of scattering experiments like Rutherford did. Okay, we bombard protons and neutrons with electron probes. We're very confident that electrons are infinitely small, point-like particles with no internal structure. So any structure we see comes from the structure inside the proton. And so if we look at the distribution of what's happening, now we have a diagram showing us, in terms of our understanding of nature, what's happening. When an electron scatters off the proton, that happens via the exchange of a photon, and that photon interacts with whatever is inside the proton, if there is something inside the proton. Okay, so if the proton was itself a point-like particle, then the photon would always be interacting with a point-like particle. The charge distribution in space would be a delta function. And then there's the structure function, which is essentially the Fourier transform of the charge distribution, would be flat. If the charge distribution was spread out a little bit and had an exponential drop-off, we'd measure a dipole structure function. If there was a Gaussian profile, a Gaussian structure function, a uniform sphere has this, and the Fermi function, which is from nuclear physics, would have this type of structure function. So by measuring what happens when we do these interactions, we gain information about what's happening inside the proton. And of course, I've stolen some of my thunder already. You can see that a proton looks like this. So it has an extended charge distribution. It's not point-like. Larger nuclei like lithium have a Gaussian charge distribution. And then much larger nuclei like calcium. Calcium? No, californium. Calcium is Na, right? Californium have this Fermi function drop-off where it's a hard sphere and then a tapered edge. And this is what we've gathered by doing this type of interaction. So when we look at the things we're scattering off at higher energies in the proton, right? When the proton breaks apart, and we do this measurement by measuring the mass of these particles and the change in momentum of the electron, we get results like this. And the important thing to notice is it's not flat. So this tells us that we're scattering off an extended object. This is showing that if we describe this just in terms of the idea that we have, that this is an electromagnetic interaction, that there is a photon, that photons have spin 1, that fermions have spin 1/2, that we're scattering off a spin 1/2 fermion, then we can build up the structure function as having two components. One that's essentially a magnetic interaction because of the motion of the particles, and one that's an electrostatic interaction. And what we measure fits very well with that. So we're very confident that until quite high Q squareds, the data matches this idea of what's happening.
Sorry, Sahal.
What gets really interesting, yes.
There is a wonderful question exactly about the subject. The fact that the quarks are never bound, never free, is mathematically proven, or maybe it is just because we cannot afford it experimentally?
The theory assumes it based on the experimental observable, right? I mean, these things go together. So the theory that describes it in a way that allows for this. So these ideas of, for example, asymptotic freedom and confinement, yeah, they were seen before they were described by the theory. But at the moment, the theory does include that.
Thank you.
I'm not sure if that's a clear answer. Does somebody want to ask the question again, maybe slightly differently, or remind me so I can give a better answer, or was that okay?
I think that's okay. I mean, unless the person will reformulate it, we'll see.
Okay, so let's keep going for a few more minutes. So the two plots on the right are the ones we've just been looking at. The one on the left is showing us as a function of how much energy is transferred from the electron to whatever is in the proton, what we see from this structure function. And the amount of energy is going up. We see this label has this value W. It starts at 2, where it has this slope. Then it goes to 3, where it becomes less sloped, and then 3.5, where it becomes even less sloped. It doesn't ever actually become flat because of the details of the strong force, because the gluons have color and they interact with each other. But this type of plot and further measurements like this are why we say that quarks, the things inside the proton that we appear to be scattering off, the quarks and gluons, we think are point-like particles, right? Because remember, point-like particle would give us a flat structure function. And as we turn up the energy, it gets flatter and flatter. And that starts to break, but we do understand that. And again, it's just more complicated honors level stuff. So we're not going to talk about it too much more. In terms of confinement, the evidence for quarks that we see is in a process like E plus E minus going to QQ bar, right? This is something that's allowed in quantum electrodynamics. It should happen. We never see it. What we see in our detector, for example, if we think of our electron beams colliding into and out of the page, we see these jets of collimated particles back to back. And we identify this with a pair of quarks emitted back to back in the transverse direction. And as they move apart, there's this process of a shower, like an electromagnetic shower, where the quarks radiate off gluons, which pair produce more quarks, and we end up with 2 jets of particles. So this is how we see and identify quarks, and this is directly tied to the idea of confinement. And as the 2 quarks move away from each other, there's more and more energy stored in the field between them. And so they generate more quarks from that energy and that mass. And we end up seeing these 2 jets. So that's the experimental evidence.
Sorry, Sahal.
The evidence
Which slide we're supposed to see?
I beg your pardon?
Which slide we're supposed to see? Because at least I'm still seeing evidence for quark lepton nuclear scattering.
Oh, no. So that's not what you're supposed to be seeing.
Yes, because when we're talking about the
It's
showers
supposed to
of
be
particles, I was thinking, yes.
Yeah, no, let me stop sharing and then start sharing again. Nope, it doesn't want to share. That
Do
is...
you want me to try sharing your slides from my side, Sahal?
Let me try one more time. There we
Yeah, something is happening. Yep.
Okay.
Okay, so that's where we were. And then this is what I was talking about with E plus E minus to QQ bar. And we see our jets of quarks in our detector in the transverse direction, back to back. These guys that are curving off are because there's a magnetic field and they have low momentum. If a gluon is produced, remember we can just add another one of these vertices here. Then we end up with a 3rd jet. And that was essentially the first evidence for gluons. And I think there is not enough time to make this last point, which is how why we know that there are 3 different colors of quarks. But this will be uploaded and you can read it and send me an email, or we can talk about it next week for a couple of minutes. I think this is the end of our time. Thank you. I'm sorry about the technical difficulties. I hope this has been informative, and yeah, questions.
Yeah, thank you very much, Sahal. Thank you very much for another very nice lecture. And we will post then the slides on the NITheP website so that everybody can give a look at it for a second time. Ilya, are there more questions to Sahal? And maybe since our group is not that big, we can allow a few people to raise their hand and ask their question directly.
Right now, there is no more questions and no raised arms, but maybe we can give a couple of minutes to people to think. And meanwhile, the participants are requiring some standard reading material, Sahal, so which we can also add to the description of your lectures in the YouTube channel. Can you please recommend some standard books? And ideally, you know, like undergrad level and kind of honest level and research level, something like that. So because I don't know, Peskin Shredder is here and so on and so forth.
I'll mention a couple of books. Yeah, I'll just email them to you and Francesco to put up somewhere.
Okay, that would be perfect. Thank you.
Maybe you could also write the titles on the last slide of the next talk.
Yes,
so they're all together. Yeah. But we can post them also separately, no problem. Yeah. It will be a pleasure. Yeah. Okay, it seems that there are no more questions, or sorry, yeah, there is no questions in the Q&A, and there are no questions in the chat, and nobody raises their hand. So I think, Sahal, we can thank you again for here we go. No, sorry, this is just a thank you from one of the participants for a wonderful talk. So Sahal, thank you very much again for your time and for sharing your knowledge of elementary particle physics. And we will see you again next week at the same time in the same Zoom. Yeah. So thank you very much to the participants, and we are looking forward to see you again next week. Thank you.
Thank you all for coming. Bye.
Bye, Sahal.
Thank you.
Thank you very much. Thank you as well. Yeah. Bye.
Bye.